I'll be presenting this work. It's called Tightly Seal Your Sensitive Pointers with PACTight. And this work was accepted and published in Usenix Security 2022. Um, so let's start off with talking about ARM. ARM processors have been increasing in popularity in recent years due to their expansion into the desktop and the data center market. And this expansion exposes ARM more than ever to security attacks. ARM has always been more on the embedded side. Now they're going into the data center and server markets. And it's becoming increasingly important to have effective and efficient defense mechanisms, specifically for ARM in these environments. And many of these security attacks are due to memory corruption vulnerabilities. And as was mentioned in the previous talk, they're very serious. And in a study that was done by Microsoft on its products, they found out that 70% of all the security bugs in their products are due to memory safety issues. And 30% of bugs that are in Google's open source are also due to memory safety issues. So let's talk about some background and related work. So let's first off defining what memory safety is. What we have here is a visualization of the virtual memory with a memory object allocated and a pointer that points to it. And pointers are used to access data in memory. And memory safety means that memory objects are guaranteed to be accessed only between their intended bounds. And this means that the pointer should not be allowed to access any data outside of those bounds of the allocated one. And also, memory objects should only be allowed to access should be accessed only during their lifetime. And so the pointer should not be allowed to access this memory object if the memory gets deallocated. Also, the memory object should only be accessed by a pointer of the same type of the same or compatible type. And thus the pointer of type B should not be allowed to access a memory object of type A. These are the rules, but attackers always violate these rules. So how can these rules be violated to violate memory safety? First of all, violating bounds can be done by a buffer overflow, in which an attacker stores more data in the buffer than its capacity. And this leads to an overflow that corrupts other data in memory. And this is due to the fact that C and C++ semantics allow this type of behavior. They don't check bounds in the language itself. And if it's carefully corrupted, the attacker can exert extremely powerful attacks. And I'm going to demonstrate a few examples of these attacks in the coming slides. The next violation violates the lifetime, and it's referred to as a use after free violation. And as the name suggests, this violation happens when an attacker uses a pointer to an object after the freed object has been deallocated. And this is dangerous if the attacker can reuse that pointer to point to something that is malicious. And the last type of violation is a type confusion violation, in which the attacker uses a pointer of a different type to the object that they are pointing to. And this is utilized in the case where there is some sort of sensitive code that is in the memory and it isn't easily corruptible. And so corrupting a pointer that is not sensitive to point to that sensitive code would be easier. And an example of this happening would be when the program takes a specific input and the attacker uses that to violate to exert type confusion. So here I'm going to introduce two attacks that are based on violating memory safety: control flow hijacking and use after free attacks. Control flow hijacking attacks aim to maliciously change the legitimate control flow of the program. And this can be done by corrupting indirect calls or jumps that are in the program, or corrupting return addresses. And this allows the adversary to execute an illegitimate control flow transfer that can, for example, reach a system call illegitimately. And the next type of attack is a use after free attack. Use after free attacks are a type of temporal attack. These types of attacks exploit the dynamic memory and the heap allocation that's in memory. A pointer is allocated on the heap, and it can be used by the program legitimately. But when the memory itself is freed, and the pointer itself becomes what is referred to as a dangling pointer. And this can be exploited by the attacker to violate the memory and execute a memory corruption vulnerability attack. So let's take a look a little closely exactly in code. How does this happen? So here's a code example showcasing how the attacker can hijack the control flow of a program via a specific memory corruption vulnerability. It is very well known in the C community that string copy is a very dangerous function to use, and a lot of people don't use it anymore. However, this is just for demonstration purposes. The function handle underscore rec allocates several variables on the stack, and including this function pointer called func. This function pointer is then assigned a legitimate value by the program. However, the string copy function immediately following this assignment allows the attacker to overflow the buffer due to the layout in the memory. And this overrides the function pointer with a value, with a specially crafted malicious pointer. So the attacker overrides the entire buffer, but for that specific region, a specially crafted pointer is placed in there. And this is, you can easily do this. This is not really that hard to do. And then when the function gets dereferenced later, this jumps somewhere else other than what the user has intended for. And this is dangerous because it can lead to what's referred to as arbitrary code execution, in which the attacker can execute whatever code they want. Another code example showcases how C++ virtual table pointers can be exploited in a use after free scenario. So this is more of a use after free attack than the control flow hijacking attack. In this example, an object A is allocated on the heap. It is then deleted, and object B is allocated on the same heap region that object A is in. And if func1 and object A gets dereferenced, execution mistakenly happens on object B's func2. And this type of execution can allow the attacker to call arbitrary functions. So they can call whatever functions they want, just replace it, and then they're able to maliciously execute the program. And this deviates completely from the intended execution that the program should be done on. So in order to help combat abusing pointers, ARM released pointer authentication. This is a hardware security feature that relies on utilizing the unused bits of a 64-bit pointer. So when you have in the address space, pointers are either 32-bit or 64-bit. And in 64-bit space, not the entirety of the 64 bits are used. Only a fraction or a portion of it is used by the OS in order for to be used. And so there's a part that is not used. And so what pointer authentication does is that it generates what's called a PAC, or a pointer authentication code, similar to a MAC, by a cryptographic hash function. And this PAC cannot be calculated without the secret key. And it's placed on the top unused bits of the pointer. And then when you want to use the pointer, you authenticate this PAC first to make sure that the pointer wasn't manipulated. And then if it's authenticated successfully, the pointer can then be used. So how does the mechanism work exactly? So there are two main primitives. The first is signing, where the pointer or the cryptographic hash algorithm takes a secret key, it takes the pointer itself, and it takes a modifier. And the modifier is provided by the user. It's provided by the programmer himself. And the algorithm then computes the PAC and it places it on the top unused bits of the pointer. And then when you want the pointer needs to be authenticated, the algorithm takes the same inputs again and it regenerates the PAC. If the PAC matches, then the PAC is cleared from the pointer and the pointer can be used. However, if it doesn't match, the top two bits of the pointer are flipped. And when the top two bits of the pointer are flipped, this renders the pointer to be completely unusable. And any dereferencing of this pointer results in a segmentation fault. And so effectively stopping any type of attack that the attacker would want to do. So there have been several defenses that have been proposed in the literature recently. I'm going to quickly go over their main points of interest, but if you guys are interested, you'd be more than welcome to read the full papers. The first one is called parts CFI, which enforces forward and backward edge control flow protection. And the modifier that they use is the stack pointer, combined with a function ID for return addresses and a type ID for indirect code pointers. PACTight is a defense mechanism that protects the backward edge, and its modifier is the previous chained return address on the stack. So what this mechanism does is that it uses all of the previous return addresses as the modifier for the next return address. And so if you violate that chain, the authentication will fail, and this will allow the attack to be detected. And last, we have a paper called PTAuth, which is a temporal defense mechanism that protects the heap. Its modifier is a generated object ID for each and every heap object allocated. So for every heap object that's allocated, there's a specific object ID that gets fed into the modifier to generate the PAC. One quick observation, if you guys have seen in all of these defense mechanisms, is they really emphasize the modifier, or the discriminator, or the salt, if you're talking in more crypto terms. This is because it can be made complicated enough or simple enough, depending on how unique you want the implementation to be. And so this is what we focus on in our work here as well. So some of the limitations that are present in the current state of the art, first of all, is reliance on a modifier that can be repeated. So if you just take the type of the pointer as your modifier, this can be repeated because the type repeats within the pointers in the application. And this means that the attackers can reuse those packs that are generated in another context. Another limitation is needing a forward edge CFI technique to be present with the pack defense mechanism. So PACTight only protects return addresses. It does not protect control code pointers. And so an attacker can completely bypass the instrumentation by just abusing the forward edge CFI technique or by just abusing code pointers instead of return addresses. And so it's necessary for this type of defense for PACTight to have a forward edge CFI technique. And lastly, a constrained threat model. So PT-auth, which is the last defense mechanism that I talked about, allows only for an attacker that has arbitrary write capabilities. So an attacker can have arbitrary write, arbitrary read, or arbitrary read-write capabilities to attack an application. And so the PT-auth defense mechanism only allows for an attacker with arbitrary write, because if the attacker can do arbitrary read, they'll be able to read the object ID and they'll be able to completely bypass the mechanism. And so I'm going to introduce our solution, PACTight. So based on the limitations that I've mentioned, we identified 3 security properties in pointers that if they are enforced, they completely prevent any type of, they completely protect pointers from being abused. They are unforgeability, in which a pointer always points to its legitimate object. Non-copyability, meaning a pointer cannot be used in a location other than its legitimate one. And non-dangling, meaning that a pointer cannot be used after the object has been freed. And enforcing these 3 properties tightly seals the pointers from illegal use. So let's take a closer look at these 3 properties in order to better define them. So the first property, forgeability, means that a pointer that points to a specific object becomes corrupted with a forged pointer that points to another object. Copyability means that a maliciously copied pointer can still be legitimately used to point to an object. And dangling means that the pointer of a freed or a malloced object, a freed or a realloced object, still points to that object and can be abused by an attacker. And so these are the 3 properties that we aim to enforce and we aim to defend against. And there are very powerful memory corruption attacks that are a direct implication of violating these 3 properties. An attacker can generate valid packs with forgeability, they can reuse valid pointers with copyability, and they can reuse invalid pointers with dangling. And so the importance of these properties stems from the fact that in order for you to hijack control flow and to execute a memory corruption attack, you must violate at least one of these properties. And so PACTight, the solution here, tightly seals and guarantees that you cannot violate any of these 3 properties. And it also overcomes the limitations of the previous approaches. The non-copyability property prevents any packs from being reused again. PACTight protects all the globals, stack variables, heap variables, so it protects all types of memory. It's not constrained to one type only. And PACTight assumes a strong threat model, which allows the attacker for both arbitrary read and write. So let's take a little bit of a closer look into the design. So how will PACTight enforce these 3 properties? So PACTight relies on the pointer authentication modifier, as I mentioned before. And this is the modifier that is used by the cryptographic hash algorithm to generate the pack. And the main reason that we rely on it is that it's user controlled, and it can be made complicated or complex enough in order to generate a unique pack. And any modification to this modifier will result in a completely different pack, and thus a violation would be detected. And so we propose to blend the address of the pointer and a random tag that is associated with the memory object. So we have 2 things, the address of the pointer or the location of it, and the random tag associated with a memory object. And this random tag gets removed when the object gets deallocated. And so for signing, we incorporate these elements into the modifier, and for authenticating, we incorporate these same elements back in. So let me explain now how this specific choice allows us to enforce all 3 properties. So first of all, the pack mechanism includes the pointer as one of the inputs to generate the pack. And so a forged pointer, which would be different from the other pointer that was used, would generate a different pack and thus would cause a violation right away. And so the pack mechanism itself enforces the first property, the unforgeability property. For the non-copyability property, the location of the pointer being included as part of the modifier means that any copy pointer will generate a different pack on authentication, right? And this results in a mismatch on authentication. So even if you copy a pointer, even if the pointer has the same exact value, the location of the pointer is different. It's two different memory locations. There's still two different pointers. And so we have the location of the pointer included. And so even if the pointer itself is the same, which means that it can violate the first property, it will violate the second property now. So the non-copyability property can be enforced. And to enforce the non-dangling property, PACTight assigns a random tag to the pointer, right? And this random tag is generated upon allocation, and it is removed upon deallocation. And this allows the life cycle of the object itself to be tracked. And a dangling pointer being used will not have a tag, right? There won't be any tag for a pointer that is dangling or that has already been freed. And this allows the pack itself to be different. And this type of violation will be detected. And so in this, yeah, like for example, let's say an attacker has a pointer that they control, right? A pointer that they control where it jumps to, right? And they want to use this pointer in a specific portion of the code where another pointer is being already dereferenced. Forgeability means that they're just going to take that pointer, overwrite the other pointer in that specific memory location, and then when that memory location gets dereferenced, it jumps to the attacker's location, right? This forgeability means that you're using a completely different pointer. The pointer value itself is different. That would be a type of attack in which the attacker would be able to do this. And enforcing this property means that it's different. So let's say the attacker overwrites the pointer but leaves the pack as it is. The pack, when it was originally signed, it used the old pointer. And so the new pointer now, when it's being used to generate another pack, it's going to be different. And it's going to be, yes, exactly. The stack smashing can be one example of that.
So it's essentially some tampering of a legitimate.
Yes.
Pointer.
Yes, exactly. The tampering of the pointer itself. And the other two properties, let's say the attacker has the exact same pointer value, but they just copy it, right? To overcome the forgeability. No, we still prevent against this by including the location of the pointer in. And so this way the attacker wouldn't be able to do it. And let's say the attacker tries to overcome this as well by using the exact same pointer, same location, but that pointer was freed and is no longer being used by the programmer, but it wasn't deallocated properly. The attacker can still try to use this, which overcomes the first two properties, but it will violate the third property. And so from our analysis, in order for you to do a memory corruption attack, you must violate one of these three properties. And so we tightly seal all pointers from any types of violations. And so taking a look at the structure and the overall design, PACTight security properties are used as a framework to instrument programs. And the instrumentation depends on how broadly they're applied. And so PACTight is composed of the PACTight LLVM pass. LLVM is a compiler infrastructure in which the Clang compiler is a part of. And so PACTight, you can think of it as a customized compiler that is used to compile programs and to add the security instrumentations into them. We do this by doing what's called static analysis on the LLVM's intermediate representation. So the compilers have their own representation that they take a look at in order for them to compile the program to. C or C++ programs compile to it, and then they go to assembly or machine code or whatever it would be. This is a simplified example for the sake of the presentation, but I have more examples that are in the paper if you guys are interested. Let's talk about the PACTight defense mechanisms. PACTight can be easily applied to a variety of scenarios. And in our case, we apply it to 4 specific defense mechanisms. We protect control flow integrity. We do C++ vtable protection. We do what's referred to as code pointer integrity and return address protection. And I'll only be explaining code pointer integrity, but we do cover the other ones as well in more detail in the paper itself. So PACTight CPI, or code pointer integrity, protects what's referred to as sensitive pointers. And sensitive pointers are all code pointers and all data pointers that point to code pointers. So there's 2 types of pointers, a code pointer or a data pointer. Code pointers are mainly like function pointers or return addresses or that type. And data pointers are pointers that store data. And so sensitive pointers in this case are all the code pointers and data pointers that point to it. And we authenticate the pack at a sensitive pointer so that we can guarantee that it only executes at its legitimate site. And we identify all sensitive pointers using what's referred to as LLVM's type information. So we recursively look inside elements of a struct or a composite type in order to find all the pointers that we need to instrument. And PACTight is implemented as an LLVM compiler pass with 3,237 lines of code. This does all the instrumentation for all the defense mechanisms except for the return address mechanism. Return address is done in the backend in the machine IR or the machine intermediate representation. So LLVM has two representations for code, either intermediate representation or machine intermediate representation. Intermediate representation is closer to human readable. Machine intermediate representation is closer to assembly. And this is done with 121 lines of code. And the library for PACTight primitives is 656 lines of code. And we also use link time optimization, which is an optimization that is done to combine all the source files into one single file. So if you have a very big program and you combine them, link time optimization combines them all into one big source file. And this is good because it allows the compiler to optimize any accesses that are done before we do our instrumentation. And so let's take a quick look at the evaluation of PACTight. So first of all, we answer two questions. How effectively is PACTight against security attacks, and how much performance does it impose? So for the security evaluation, we evaluated it against three CVEs: a heap-based buffer overflow, a use after free exploit, and a buffer overflow vulnerability. And these are in the libtiff and in libpng and in Python. And so these are real attacks that exist out there that we've been able to test PACTight on, and we're able to successfully defend against them. And more details on the exact way of how we do this and the code is in the paper as well, if you're interested. For the performance evaluation, we ran it with three sets of benchmarks. We ran it with the spec CPU 2006, which is the industry standard. It's now 2017, but at the time it was 2006 that we used, the industry standard for measuring, for benchmarking, NBench set and CoreMark. And we also ran one real-world application, Nginx, which is a web server. And we here see the numbers for it. And as you can see, the overhead is very minimal across the board. And I will also say 4% for PACTight CPI includes also all of the other mechanisms. So it includes everything, and that's around 4% overhead. And so it's pretty performant in the tests that we have run. We also evaluated the memory overhead of PACTight CPI, specifically on the spec benchmarks, and it's 19% memory overhead on average. This is because when we allocate the tags, we have an external memory for them. And so in certain programs that are very heavy in allocations on the heap, you can have the memory overhead gets very high. One of the programs here does like maybe 200 or 300 million heap allocations. So it increases the memory overhead by quite a bit, but still 19% on average is considerably low compared to some of the others out there. So the overhead comes from two places, comes from the PAC mechanism itself, and comes from accessing the tags. The tags are stored in memory. The way I implemented it is a linear open addressing hash table. So the access is pretty fast. It's an O of 1. However, it is still like when you do a lot of them, it gets costly very quickly. Memory overhead, like the thing is, it depends. PAC is just a mechanism, and it depends on how you use it. So if you protect all return addresses, that's the number. If you protect code flow, control flow integrity, that's another number. If you protect, depends on how many pointers you would protect. But if we're talking just the PAC without the hash table, so let's assume I'm removing the hash table from the question, I would say this would go down by maybe 60%. So the hash table by itself contributes to about 60% or 65% of the total overhead. And the main reason that the PAC can sometimes be expensive, even though it's in hardware, is because there are programs that that execute pointers in a loop. And so you have to authenticate and sign consistently. So that's where majority of the overhead comes from. But of course, in the case of just the PAC only, there would not be any memory overheads. There would just be a performance overheads, the runtime overhead. So now I'll conclude. I've introduced PACTight, which is an efficient and robust mechanism that utilizes ARM's pointer authentication primitives to guarantee what I call pointer integrity. We identified the three security properties that we enforce, and we showcased the defense mechanism with the PACTight itself with 4 defense mechanisms and protect a wide variety of security sensitive pointers. And we evaluated it against real world and synthesized attacks, and there are more details on those in the paper. And we showcased its low overhead on a variety of benchmarks. And thank you very much. And it's open source on GitHub, so you can go in and check it if you want.